So we're going to develop a general equation of groundwater flow, and we're going to do that by balancing water coming in and out of a control volume. So if we recall, a control volume is just a box where we keep track of everything that comes in and everything that comes out. So this is our control volume. As I said, it's just a box. It has dimensions of delta x, delta y, delta z. So we wanted to see how water comes in from all sides, but that gets pretty complicated. So I'm going to start with just keeping track of how water comes in from this direction and out this direction, so only in the x direction. So we're going to look at the Darcy flux in and the Darcy flux out, only in the x direction. And then when we're done, we'll just sort of generalize this for all three directions to make our total continuity equation. So we have in and we have out, but we want to be able to relate those two. And so let's start by thinking about in the x direction. What the total flow rate is. Now remember, this is a Darcy flux, so it has units of length per time. And what we want is flow rate. So if you remember, the flow rate is going to be the Darcy flux times the cross-sectional area, right? So the total flow in here is going to be Q in is equal to lowercase q in times delta y times delta z, right? And then Q out is equal to the Darcy discharge out times delta y times delta z. What we're going to want to do, though, is we're going to want to relate the discharge out to the discharge in. And so what we're going to do is we're going to express out in terms of what's coming in and how much that Darcy flux changes as you move along this delta x direction. So this is sort of like if I tell you that you're going to drive and you start at 10 miles an hour, and I say that every mile you're going to go a mile an hour faster, right? So you know that at the end of 10 miles, you're going to be going 20 miles an hour. So let's see if we can make an expression that sort of looks like that. And so we'll start the balance as Q in times delta y times delta z, right? So that's what's coming in. And then we're going to calculate what's coming out as, so we want the flow rate in minus the flow rate out. Q in minus Q out equals the change in storage with respect to time, remember? So we want Q in minus Q out. So then Q out is actually going to be Q in plus the rate of change at which that flux is changing. Right? So dq dx times delta x. So it's changing at a rate of dq dx, and it's changing over a distance delta x. And then we're going to take that and we're going to multiply that times delta y delta z again. So you may notice here that rather than using the usual d we have for derivatives, we're using this symbol for partial derivatives. And that's because this discharge is only changing in the x direction right now. We're saying that we're calculating the rate of change in the x direction, not the y direction, not the z direction. Otherwise, you can basically treat it as if it was a regular derivative. And so on the, excuse me, on the right-hand side, we're going to have the change in volume with respect to time, right? So we always use this general term storage when we get started, but now we want to see specifically that we have the change in volume with respect to time, and that's the volume of water. So we have the flow in, the flow out in this water balance, okay? So notice if I multiply this through, I'm going to multiply delta y, delta z times here, this q in, this is delta y, delta z, q in, and so these all drop out, they cancel each other out, and you end up with the change in discharge with respect to x times delta x times delta y times delta z is equal to change in water volume with respect to time. So that's always cool when we can make this simpler somehow. And so let's take a look at what that would look like if we did this in all directions. I'm not going to put arrows in all directions because that gets awfully complicated. So I'm just going to write it out. So we have, and I'm going to gather the negative signs. We have the change in discharge with respect to x plus the change in discharge with respect to y plus the change in discharge with respect to z. And that's all going to be times delta x times delta y times delta z is equal to the change in volume with respect to time. Okay? So now what we have is a bunch of discharge, and that's not terribly helpful because we can't measure Darcy flow in the subsurface. What we can measure is hydraulic head. So you should know by now, how do we relate hydraulic head to specific discharge? We do it with Darcy's law. And so Darcy's law is going to be Q is equal to minus hydraulic conductivity. So notice that we had directions for these. So this is the hydraulic conductivity in the x direction, for example, times the change in head with respect to x. And then we have, of course, y, and we have z. Oops, I'm getting ahead of myself. We have the discharge in all three directions, right? So I can go ahead and I can substitute that in, and we're going to end up, notice that there's a negative sign in front of all these Darcy's law, and so that's going to cancel this negative sign, and so we're going to end up with the change in the x direction of hydraulic conductivity in the x direction times head in the x direction plus the same thing in the y direction plus the same thing in the z direction and nothing much has happened here on the right except that notice we have all this delta x, delta y, delta z. So let's bring that over here. And we still have the volume with respect to time, a little close to the edge. So notice that delta x, delta y, delta z is just the volume of the control volume, right? And so we can say that this is the total volume, whereas this is the water volume. All right. So that's essentially our continuity equation, except we want to work on what's on the right-hand side here a little bit. And to do that, we're going to have to remember the equation that we had that related this storage here to head, because we want everything related to head, not volumes of water. And so we had this definition for specific storage is equal to 1 over the control volume times the change in water volume with respect to head. And so that means we could substitute that in here and come up with the final expression for the continuity equation. Where we substitute in, if we substitute in this expression here, notice we have this expression for time and we have this for head. And so when we substitute this in, we end up with the specific storage times the change in head with respect to time. And so this is our continuity equation that accounts for flow in and out of that that control volume. And so we have water flowing in and out of the control volume, and then we have water coming from storage. And remember, S sub S is specific storage. So we're going to play with this a little bit, but this is the starting point.